All right, so in this section, we're learning three new sets of identities, three new sets. And you do have to commit yourself from the very beginning, like commit it to like, it's a new start. We just took this test. Maybe I didn't do so well, but it's a new section, new identities. I can learn these new identities, and I'm going to learn these identities, and I'm going to practice on my worksheet, right? So the first ones are called the double angle identities. And what they allow you to do is to express an angle that's twice as big in terms of an angle that's half as big. So we call that angle 2 times x. And notice we can express it in terms of single angle x. So that's the first one you want to memorize. Sine of 2x is 2 sine x cosine x. 2 sine x cosine x. Think about it as pulling the 2 out front, right? You're pulling the 2 out front and adding a cosine. If you need help with memorization, pull the 2 out front and add a cosine. Now the cosine one, cosine of 2x has three different ones. You don't have to memorize all three of them. All you got to do is memorize this one right here. That's the main one. And it looks a lot like what other identity? Yeah, Papa Pid. It looks a lot like Papa Pid. The only difference is there's a minus sign in there. And the minus is very important. It has to be the sine squared that's a minus. The other two come from the Pythagorean identities themselves when you make replacements. And then tangent, of course, is still sine over cosine. But if you think about the other one, it's 2 tangent of x over 1 minus tangent squared of x. Okay? So where can you go to help yourself memorize these things if you like flashcards? Quizlet, right? If you go to Quizlet and you search Corpy's world, two words, you'll see there's not only unit circle stuff there if you want to brush up on that, but there's fundamental identities, and then there's a couple that say all identities. All right, let's try it out. Prove the following double angle identity. Well, we're going to draw a line down the middle. And although I haven't graded y'all's tests yet, I think most of y'all probably have that part mastered, right? The line down the middle. If only I gave a check for that. Now here's what we're going to do. We're going to use our our composite identity to write 2x as x plus x. Cosine of 2x is x plus x, right? Now I can use my composite, which is selfish cosine. Cosine, cosine, me. Change the sign, sine, sine. So we get sine x, sine x. And now, of course, that becomes cosine squared minus sine squared. And that's the main identity that y'all need to memorize. It comes straight from the composite identity, right? Cosine of 2x is equal to that. But we need to go a little bit further. We look on the right-hand side and we realize that I need to get rid of my sine squared and pick up another cosine squared. So I carefully put parentheses around the sine squared, and on the next line, I write it as cosine squared of x minus 1 minus cosine squared of x. So I do that Pythagorean substitution. And parentheses are really, really good to have when you're trying to make a substitution. Now if I distribute, I get cosine squared of x minus 1 plus cosine squared of x. And lo and behold, I have like terms. Cosine squared plus cosine squared is 2 cosine squared minus 1. And you look on the other side, and you're done. QED. Yeah. And you could get the other one in terms of sine just by replacing cosine squared with 1 minus sine squared. Okay, it works. Memorize it. I had a banana this morning too. That's your stylus? And it works? Really? Huh. I have an apple stylus and you have a banana stylus. Number 2. Cosine of x, the single angle x, is negative 2/3, and sine is greater than 0. Find the cosine of 2x, the sine of 2x, and the tangent of 2x, and blah, blah, calculator. All right. First things first. I want to figure out what cosine of 2x is. All I know right now is cosine of single x. That's what I know. So you ask yourself, is there a way to express cosine of 2x in terms of cosine of 1x? And the answer is yes. There's 3 different ways you can write cosine of 2x. The one that is the one we want, if you come back up here, is the one that's exclusively in terms of cosine squared. Right there. 2 cosine squared minus 1. And you know that's available because you memorize it. Now I can work straight down and plug in. This becomes 2 cosine squared minus 1. And what am I plugging in for cosine? I'm plugging in a negative 2/3. How do you get that little toolbar that's the second toolbar at the top that has your favorites, or on the right? Do y'all know? If I go to here, top, oh, the star. Oh, I see, I see, I see, I see. I've never done that before. You drag it over? No. Oops. Y'all are helping me. I'm learning. Click the line. But there's no colors in it. Oh. Oh, okay. Click the color. Okay, let's try that. Click the color, then click the star. Hey, you know what? I'll figure it out later. I'll figure it out later. Yeah, I think so. That sounds like what it should do. There we go. Minus 1/9. So we work all the way down, and after we use the identity, it's just a matter of plugging and chugging, plugging and chugging. Now let me kind of give you a taste of what we're doing here. What we're doing is we say we have an angle x that lives in quadrant what? If cosine is negative and sine is positive, what quadrant is that? Sine is positive and cosine is negative, so that's got to be over here somewhere. So let's say that this is x. Let's hypothetically say it's about, let's say it's about 100 degrees, just to kind of give you an idea. And if we drop our perp right here, we know cosine is negative 2 there. We know it's 3 here. And this is going to be the square root of 5 if you use the Pythagorean theorem. So we have all three sides. But what are we doing here? We're finding the cosine of an angle that's twice as big. An angle that's twice as big would be somewhere down here, like 100 times 2. 2x would be around 200 degrees. And what do we know about a triangle down here in quadrant 3? What do we know about the cosine? Is it also negative? It is, right? It's negative 1/9. And we can see that it's negative because it's in quadrant 3, right? So that would be 2x would be right here. Let me move this around. Our single angle is 100. The double angle would be 200. Everyone good so far? Now I'm going to find the sine value right here. That's what's next. What should the sine of the sine be? SIGN, positive or negative for the double angle? If the double angle lives in quadrant 3. Should be negative, right? Let's try it out. Sine of 2x is 2 sine x cosine x. So I don't really have the option like I did for cosine to write it exclusively in terms of cosine. I have to have the sine as well. But you know what? I have the sine because I have the y value. I used the Pythagorean theorem, 9 minus 4 square root of, and I got the y value, square root of 5. So let's go ahead and plug in. The sine of x is going to be the square root of 5 over 3, and the cosine x is negative 2 over 3. So this ends up being negative 4 square root of 5 over 9, which is in fact a negative number. Yep. And then the tangent, the last one, what should the sine of the tangent be? Positive or negative of the double angle if we're in quadrant 3? Well, it's negative x and negative y. So it should be positive, right? Let's see if it is. Tangent of 2x is going to be 2 tangent of x all over 1 minus tangent squared. So we got to memorize that one. And now I'll plug in. This one's going to be fun. Watch. What's the tangent? It's square root of 5 over negative 2. All over 1 minus, parentheses, the the square root of 5 over negative 2 squared. At the beginning of the year, you might have been afraid of an expression like that, but now you're excited, right? You're like, ooh, 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 complex fractions and radicals. Let's simplify that. That's going to be negative square root of 5 in the top, and the bottom I get 1 minus 5/4. And now all I got to do is get rid of the complex fraction. So in the bottom, I have negative 1/4, and that gives me, when I state change flip, 4 square root of 5. So it was negative the whole way down, and then on the very last line, it became positive. It became positive. That's like you being negative all week long, Monday, Tuesday, Wednesday, Thursday, and then right at the end, boom, on Friday, you're positive again, right? Because you're like, yay, it's almost time for no school for 2 days. Y'all don't think that way, do you? Golly, no. You're like, darn it, it's the weekend again. God, I survived another weekend. Thank goodness I'm back at school. All right. Questions on that? Comments on that? Sure, certainly you have comments. How would you verify that on the calculator? You would just pick an angle like I did here with 100, and you would plug it into the beginning and plug it into the double angle identity. Yeah, I don't want to really get into that. We know we're right. It's hard for me to pull my calculator up. That's why I don't want to do it. All right, example 3. We're going to be using more of these identities, and you're going to hopefully learn to love them. I didn't like coffee the first 10 or 1,200 times I drank it, but I'm getting used to it now. It's part of my morning regiment. Write cosine of 3x in terms of cosine of 1x. How am I going to break down the angle of 3x and put it in terms of x? Do we know a triple angle identity? Have I taught you a triple angle identity yet? No, but we do have the composite identities. We can write 3x as 2x plus 1x, right? Yeah, we can. And now we'll use the selfish cosine composite identity. Me. Cosine of 2x, cosine of 1x. Change the sign. Sine of 2x, sine of 1x. Okay, we're getting closer. We're getting closer. I have cosine of x right here. I need to get rid of everything else and put everything else in terms of cosine. Ay, caramba. I don't know how to do that. Yes, I do. I have double angles now, and I just memorized double angle identities. Cosine of 2x is cosine squared of x minus sine squared of x. That's the only one that you need to memorize. It may require a few more steps to get where you want to go, but at least it's less memorizing, right? I'm doing that for y'all's benefit. Sine of 2x is 2 sine x times cosine of x. If you're working along here and getting your brain engaged, wrapping around these ideas, you'll have these identities memorized before the end of class just because we're using them so often. There's those two again. All right, now there's some obvious algebra, right? I can distribute the cosine. I get cosine cubed of x minus sine squared x cosine x. And on the second one, there's nothing to distribute. I just combine the like factors, minus 2 sine squared x cosine of x. Now look, I'm getting closer to having just cosine of x's. I'm getting closer. I need to get rid of those sine squareds now and turn them into cosine squareds. How do we do that? Papa Pid. Yeah, Papa Pid. So here he comes again. Papa Pid is very, very useful. So as we go down here, we get cosine cubed of x minus, parentheses, 1 minus cosine squared of x times the cosine of x minus 2, next parentheses, 1 minus cosine squared of x times cosine of x. Now, if you look at this right here, I think by the letter of the law, we have met the requirements. We have it exclusively in terms of cosine of x and the number 1, which is okay, and the number 2. But let's go ahead and simplify, because this would not be an answer choice on a test if we had a multiple choice, nor would I accept it as a final answer in a free response. Let's simplify. To do that, we're going to distribute again. Now, on the first one, be careful. We're distributing a negative cosine, a negative from the left and a cosine from the right. So it becomes negative cosine of x plus cosine cubed of x. And on the next one, we're distributing a negative 2 from the left and a cosine from the right. Negative 2 cosine of x plus 2 cosine cubed of x. Well, it's starting to look a little bit better, isn't it? Look at these rascals right here. Cosine cubed plus cosine cubed plus 2 cosine cubed. Those are all like terms, aren't they? I got 1, 2, 3, 4 of them. So it's 4 cosine cubed of x. And then the other guys are also like terms, minus 3 cosine of x. And that's about as far as we can get. We're done. We got it exclusively in terms of cosine of single power x. It took a little whittling down, but we got it. Now, this little paragraph here just says it's kind of interesting that you can write a cosine of 3x. You can write it as a cubic power of single x. Just like cosine of 2x, you can write as a second power of x. If you had cosine of 4x, you could write it as a fourth degree cosine power. So on and so forth. But it doesn't work for sine, it only works for cosine. That's why cosine is a little bit more valuable. What happened to your banana stylus?
I got 100.
Okay, what happened to your screen? Because you're not using it. All right. Example 4. We have a new number 1 priority when we're doing proofs now, because we have these multiple angles working around with us. When you're proving an identity where the angles, and look how I spelled angles. Isn't that funny? Anyone want to try to pronounce that? Analogous on one side are different than those on the other. Your primary goal is to get the angles the same. Get the angles the same. That's the number 1 priority. All the other techniques that we've learned, they fall by the wayside when you're working with multiple angles. You got to get the angles the same. They can all be single angles, they can all be double angles, they can all be triple angles, so long as they're all the same. Right now we're going to get everything down to single angles. Prove the following identity. Okay, so this could have been on the test. Not really, not yet. This could be on your next test. Yeah, on your next test. Prove. What do we do first? Draw a line. Yeah, good. Draw a line. What side do you want to start on? The left. Good. Because it's got the dense nucleus. It has an angle that is different than the others. Okay? And it's easier to tear something down than it is to build it up. So we're going to go ahead and try and get that angle in terms of single angle x. Very similar to what we just did with cosine. Ready? Here we go. We're going to call it sine of x plus 2x. Or 2x plus x. It doesn't really matter. Do I want x plus 2x or 2x plus x? 2x plus x. That's what I thought. I'll rewrite it. There we go. And now we'll use the double angle identity or the composite identity for sine. We get sine of the first, cosine of the second, sine same sign, sine of the second, cosine of the first. All over, sine x bless you, cosine x bless you. Bless you. Yeah. Now you look at the right side and you're like, hey, we're almost there. Right? Is that what you say? We're almost there. We're getting closer. We're getting closer. But you know what we still have? We still have double angle here and double angle there. That's no bueno, bless you. So let's use the double angle identity now. We get 2 sine x cosine of x times the cosine x that was there plus sine of x times, now we need parentheses here. Cosine of 2x is cosine squared of x minus sine squared of x, all over sine x cosine x. So far, so good. Inch by inch, it's a cinch. Keep your eye on your target. Are we getting closer? It looks like we're drifting further and further away, but you know what? Sometimes you have to lose sight of the shore if you want to discover new lands, don't you? Uh-huh. You know what makes this progress to me? All of the angles now are what? X. They're all single X. And that's what we wanted. So yay. Now let's just go ahead and proceed cautiously. In the first term, I can combine these cosines, so I get 2 sine x cosine squared of x. And now distribute this one over here, plus sine x cosine squared of x minus sine cubed of x, all over sine x cosine x. Now you're looking at this and you might be stuck. You might be at a loss for what to do next. So that's why you look at the other side and you're like, is there anything I can do over there? What do we notice now about all of the proofs so far? Everything is in terms of sine and cosine except the other side. It has a secant in it. So this would be a good opportunity then for you to temporarily abandon the left side and move over to the right side and see if you can kind of meet in the middle. So I'll do that. That's 4 cosine x minus 1 over cosine of x. And that's good because it creates a fraction. And now if you look at the left side, you're like, hey, the left side is a fraction as well. But it's a single fraction. It's a single fraction. And right now on the right-hand side, I have 2 terms, only one of which is a fraction. So if I put that over 1 and I get a common denominator, or I do the crisscross applesauce butterfly multiply method, I get 4 cosine squared of x minus 1 all over cosine of x. That's the same as multiplying the first one by cosine over cosine. And now you're looking at it and you're like, oh, look at this. Look at this. I got a cosine in the bottom over here, and I got a cosine in the bottom over there. Hot dog! I'm almost there. I'm almost there. Not really. What can we do in the numerator on the left-hand side? Y'all notice anything? Very good. Yes, that's what I'm noticing. I'm noticing that they all have a sign. And here's what might inform your decision. The right side does not have a sign factor in the bottom, right? The left side does have a sign factor in the bottom. And we can only divide out common whats? Factors. So let us factor out the sine of x in the top. Sine of x. I'm going to put a beefy bracket. I like beefy brackets. Beefy. 2 cosine squared of x plus cosine squared of x minus sine squared of x. Beefy. All over sine x cosine x. And now with the very light color, you can go, the signs are gone. So now the denominator is all in place. The other thing you might notice is, hey, I didn't notice this before, but 2 cosine squared plus 1 cosine squared, those are like terms, aren't they? So I can call that 3 cosine squared of x. So far, it's all over cosine. Now that's getting really, really close. The next thing that you or visualize or see is, hey, there is a sine squared in the top. And I don't want a sine squared in the top. So what can I write sine squared as down here to get rid of it? 1 minus cosine squared. Yeah, yeah. And then maybe, just maybe now when I distribute, I'll be able to get the right-hand side. I get minus 1 plus cosine squared of x all over cosine. And I'm feeling it. Aren't you feeling it? 3 cosine squared plus 1 cosine squared. That's 4 cosine squared of x. I got the minus 1. It's all over cosine. I bring my line a little further down. And what? Q, E, D. It's in the game. What happened to your stylus? I got hungry. I like that. We got it. Might a proof like that be on your next test? Heck yeah. Heck yeah. By then you're going to be bored with easy proofs like this. There is a book floating around this department where it's a whole book and all of the book, the whole book is just trick proofs. The whole book. Yeah, I think Mrs. Skurhawk has it right now. It's in her possession. All right. Any questions on this proof? Soaking it in. All right. Power reducing identities. Some of y'all are bound for calculus. In calculus, we use power reducing identities when we try to find polar areas of regions. We take something that's squared, which is kind of hard to deal with, and we turn it into something that's not squared. So these identities are called power reducing identities because guess what they do? They reduce the power. Yeah. They'll take something that's squared and they'll turn it into a double angle. So you reduce the power or half the power. You always half the power and you double the angle. That's what we do. We half the power and we double the angle. We half the power and we double the angle. So if that were sine to the fourth, we would half it and get squared, and then we would double the angle, which would be 4x, right? So half the power, double the angle. Half the power, double the angle. It wouldn't be 4x, it would still be 2x. All right. Now notice what it is. It's 1 half times 1 minus cosine of 2x. Or you can write it as 1 minus cosine of 2x over 2. I don't like that version nearly as much, but it works. So notice that it is in terms of cosine, and the cosine one is also in terms of cosine. But because this one is sine, it doesn't get to keep the positive sign. It doesn't get to stay positive. It gets the minus sign. Sine gets the minus sign. Look over here. Cosine squared is exactly the same, but cosine gets the plus sign because remember, he's greedy, so he's me, 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 me. My name is on it. It's mine. I get the plus sign. Everyone wants the plus sign. Everyone wants to be positive. But it's a half times 1 plus cosine. Now guess where these guys come from? These come directly from the identities, the identities for cosine, the Pythagorean identities, the double angle identities for cosine. Watch, let me show you. I'm sorry. Watch. If I take this, where is it? Up here. Okay. If I take that identity right there, if I take the identity cosine of 2x equals 2 cosine squared of x minus 1, and I solve it for cosine squared, look what happens. I get cosine of 2x plus 1 equals 2 cosine squared of x, and then I get cosine squared of x. I multiply by a half, I get 1 half times 1 plus cosine of 2x. There it is. There's the power reducing identity. What is it? It's nothing more than one of those three identities for the double angle for cosine rearranged. All right. And the tangent one, of course, is just 1 minus cosine of 2x, which is the sine one almost, over the cosine one. Where did the 1 half go? These both had a 1 half, right? This is basically sine squared of x over cosine squared of x. What happens to the 1 half? They divide out. And that's why we just end up with 1 minus cosine over 1 plus cosine. All right. Memorize. Look at example 5. You're going to like this one. Express sine squared cosine squared in terms of a single power of cosine. A single power of cosine, like cosine to the nth power of x. That's our goal. We can have like ones and other terms in there as long as there's no other trig functions. Single power of cosine. All right. Some of y'all want to say a prayer before we start?
Amen.
Bless this problem. Bless you. Let's go. I have double powers, one of sine, one of cosine. Guess what I need to do? Step 1, I need to reduce those powers. Let's reduce them. I'll use green for sine. I'm sorry. 1 half times 1 cosine of 2x. What goes in there? Plus or minus? Minus. Good. Good. Minus. Sine, not same sign. Yeah. Cosine they're both in terms of cosine. Cosine gets his name on them. Mine. So he's 1 plus cosine of 2x. Everyone wants to be positive. In the trig world, at least. All right, now if I multiply the two 1/2s together, I get 1/4. And what do I do when I multiply these together? What are those called in relation to each other? One of them's 1 plus, one of them's 1 minus. Those are what's of each other? Conjugates. I heard it. Those are conjugates of each other. And when you multiply two conjugates together, you get a difference of two perfect squares. Yeah. So the inner and outer terms cancel. So I'm going to left with 1 minus cosine squared of 2x. Because the inner and outers cancel, right? Minus cosine 2x plus cosine 2x cancel, boom. And then you're just left with the last one. All right, so, hey, what is 1 minus cosine squared equal to? Sine squared. Now it's just sine squared of 2x. Papa Pitt again, right? He's all over the place. Now, what's my goal? I forgot my goal. A single power of cosine. Criminy. I'm two things away from it. I have sine instead of cosine, and I have a squared instead of a 1. I think I could kill two birds with one stone, because you know I'm into killing birds. Yeah, but I don't have enough stones. Beefy bracket. Beefy. 1/2 times 1 minus cosine of what? What's the angle now? I half the power. Now I got to double the angle. The angle was 2x. Guess what it is now? 4x. Yeah. I got to double the angle. Half the power, double the angle. Half the power, double the angle. Now, if I write it as this, 1/8, combining the fourth and the half, I get 1/8 times 1 minus cosine of 4x. Is that a single power of a cosine? It's a single power because it's cosine to the first, and it is in terms of cosine. It can have numbers in there, it just can't have other trig functions. So yeah, it works. We did it. We did it. Hooray. Lo hicimos. Hooray. Y'all like these new identities? Not a fan yet. Not a fan yet. Remember my coffee story, right? Well, what if I told you there's only one more set of identities you have to memorize this year? Would that make you excited? Only one more set. What if I told you there were 10 more sets? Then you'd be like, oh, I'm going to fail every test from here on out. I guess I'm taking this again in summer school at the Apex lab. No. That's just click and get. You don't think. Half angle identities. Woohoo! Half angle identities. These half angle identities come from the power reducing identities. We just solve it for the sine of the cosine. So here we go. Sine of a half angle x is equal to plus or minus the square root of 1 minus cosine over 2. Whoa. Or I like to write it like this. Plus or minus the square root of 1/2 times 1 minus cosine. The sine one again gets the minus sign. The cosine one gets the plus sign. It's plus or minus the square root of 1/2 times 1 plus cosine. And again, all we're doing is taking these right here. Like if I solve this one for cosine of 2x, I get multiplied by 2, I get 2 cosine squared of x equals 1 plus cosine of 2x. Oh, I'm sorry. I'm solving it for this. I'm solving it for cosine. All I got to do is take the square root. If I take the square root of both sides, I get the square root of 1/2 of 1 plus cosine of 2x. And then all I have to do is replace the angles. 2x is twice as big as x, and x is half as big as 2x. So if I let 2x equal x, then x would have to equal 1/2 x. But it's all it is. It's the exact same identity. It's just solved for the more convenient version. And then the tangent, of course, is still sine over cosine. So it's plus or minus the square root of what it was up above. Now, how do we know if it's plus or minus? Because we can only have one answer. It depends on the quadrant where the half angle, or the given angle, I should say, it works as well, where the given angle terminates. Would you like to try one? No? Well, here's what I think I'm going to do. I'm going to give you the rest of the period to go to your worksheet and practice what we've learned so far. Tomorrow when we start up, I'll review all the identities quickly, and then we'll put the half angle identities into practice. I don't want to overwhelm you with all of these identities at one time, okay, with their use. So yeah, we should be able to finish tomorrow. So y'all have the period to start your worksheet. Any questions or comments? The doorbell today is kind of long, but that's okay.